Welcome to CircuitValley. I'm Gaurav. Today the video is going to be about the output performance of DISTISO6 isolated distribution amplifier. Quite a few people have been asking questions about the output performance. They are primarily interested how output of two channels correlate to one another and how is the frequency correctness and how is the phase correctness. We will verify the frequency correctness using a really high-end frequency counter, and for the phase verification we will use my TDS8000, and I'll show you now how the measurement setup looks. As an instrument setup, this is the primary clock generator. We'll be using my STG2042X as a 10 MHz source, and it is connected to my distribution amplifier sitting here. 3 other channels have been used. 2 channels are connected to one instrument and 1 channel is connected to another instrument. For measurement, I'll be using my 53220A, really top of the line. It can do various things and various kind of measurement. It can of course do the ratio measurements between the 2 channels as well. So right now the measure have been set up and it have been running for quite some time. So you can see around 1650 and 1690 measurements have been taken on both of the instruments. So the top of the instrument is measuring between channel 1 and channel 2, the output of distribution amplifier channel 1 and channel 2, and the instrument is measuring the ratio between both of the frequencies. Both of the outputs have been terminated to 50 ohm, and they have been of course selected the trigger point to 50% of the signal, which is going to be for a AC coupled signal 0 volts. So right now you can see it has taken 1676 measurements, and you can see that bin size is 81 femto. So you can see the bin is of around 81 femto. There are total 101 or 102 bins from 0 to 101. So with 81 femto and 102 bins, we got around 8.2717 pico of ratio difference between channel 1 and channel 2. On the bottom side, you got a similar result. So you got 78.67 femto per bin, and for 102 bins it will also result similar amount. Although both of the instruments are measuring totally two different signal, this instrument is measuring only the same signal. You see, I have fed in the same signal using a T-coupler, and of course both of the things have been connected to my distribution amplifier. The distribution amplifier feeds in channel 1, channel 2 and channel 3. Channel 1 is fed into channel 1 of instrument 1. Channel 2 is fed into channel 2 of instrument 1. And channel 3 is fed to channel 1 and channel 2, both of the instrument 2. So both of the instruments are measuring ratio between both the frequencies, and you can see the difference between both of the things is very minimal. So what we are measuring right now is down in the capability range, or the noise or the trigger error what you have this in what you or the trigger error what you have in this instrument. We are going into down in the noise range. So we see the channel 1 and channel 2 measurement on the top line a little bit higher, and you can see of course the bell curve itself, because it's a random distribution. So we got an error of around 8.27 pico on the top, total ratio error, and on the bottom side we got 78 into 102, a little bit less than that. So for 10 MHz, 82.27 pico of error in the ratio will result error of 82 microhertz, and of course it will down there it will result around 78 microhertz. So we have successfully verified the output correlation between channel 1 and channel 2 is exactly same as from one single channel. So this instrument or my distribution amplifier is not causing any frequency deviation between two different channels. So it's very well performing. Now I'll move this instrument and we will show you the difference between channel 1 and maybe channel 4, just to show you that there is no difference in the frequency itself and there is no relation. I have to reset the histogram. We will collect histogram for some time. I'll come back and show you what's the difference. I have reset the histogram on the first channel, and you can see it's collecting the bins. It'll take some time because I'm set to 1 second of gate, so we'll wait for some. So in few minutes we got some data collected, and you can see that we got 412 or 413 measurements now collected, and the bin size has increased a little slightly from 81 to 100 femto, and which means that you get variation of around 100 microhertz between channel to channel, or channel from different driver to different driver, because you know one driver drives 2 channels, channel number 1 and 2 driven by same driver, 3 and 4 driven by same driver, and 5 and 6 are driven by different driver. So driver to driver difference is around 100 femto for 102 bins, which results to around 100 microhertz deviation from clock to clock for 10 megahertz. Now I will show you the phase relation between two channels, and we'll go to my 50 gigahertz oscilloscope, and there I will try to do phase measurements of the scope, because the oscilloscope is only capable of very low voltages, can only display 1 volt max, so we have to limit the total input from 8 dBm to lower, so that we can get the signal frequency in range itself. So we have got our measurement setup ready. Channel number 1 and channel number 3 are connected to the primary module, and channel number 2 is connected to the trigger, because this oscilloscope needs the trigger. And you can see both of the waveforms are very neatly overlapped on top of one another, and we will see if they have any kind of phase difference and what kind of phase relation they have between them. So let's get started. So I got my phase or delay measurement setup between both of the channels. Maybe I can show you. Setup shows you delay between channel 1 and channel 2, and of course, regardless of how deep you zoom in, there is no delay between them, and there is no visible or measurable delay. Even at, we are currently at 5 picoseconds resolution, I can go very deep down, few femtoseconds, and even at those levels there is no delay visible. At least I cannot measure with this oscilloscope. And this is currently running at 20 gigahertz bandwidth. It's capable of 50 gigahertz bandwidth even. So this is the resolution of 1 femtoseconds, and even on 1 femtosecond resolution, I'm looking for if there is any phase difference between the signals. There is absolutely none. So this is the phase relation between them. These signals exactly 1-to-1 match. Even on 1 femtosecond resolution, I was not able to see any timing difference or any other kind of difference. This goes to show you the performance of my distribution amplifier. We measured that there is a almost unmeasurable amount of frequency difference between them, and almost unmeasurable amount of phase difference between both the signals. And even on different drivers, same drivers, there is no difference at all. We've measured with the frequency meter that even with the same signal, frequency meter measures around 80 microhertz, or frequency meter measures around 80 femto of ratio difference between signal, and even with our drivers measures around 2 femtosecond more on the same driver, maybe like 20 femtoseconds more on different drivers. Even that can be verified and proven that it comes down to or around a very low range of measurement capability of the instrument itself. So this distribution amplifier works really well, and works very reliably, and is proven to be very decent, because I have been using it for my lab for many years now, the first version of it, which I built into my GPSDO. So if you are interested, you can visit my website www.circuitvalley.com. That's it for this video.